All right, so we're going to put models and algorithms together by playing with the blocks. So ultimately, we're working up to the idea of carrying that we do. But there's other ways to add numbers. And does anybody know that carrying is no longer the politically correct way to refer to our way of adding? Did you know that? Anybody know what the more politically correct way is to call it? In most new textbooks, you will not see it say carrying. It's regrouping, yeah. They're going to call it regrouping. Yeah. And so that's what we're focusing on here. And the idea is, again, kids are still getting used to that base 10 place value system. They've learned things like, you know, these are my 10s, 20s, 30s, then 100s, 200s, 300s, and they're getting into thousands. They're also getting into addition of multi-digit numbers. After they spent a long time just doing single-digit numbers and starting to remember those facts. And so half the kids in the class, you go 7 plus 8, and they go 15. The other half is still counting on their fingers, trying to get up to 15, because they don't have those patterns yet. Okay, and so there's some research that shows playing with toys like this, and not necessarily my virtual ones, but the physical ones you have in front of us, that helps build these patterns in the brain so that when someone says 7 plus 8, they see 15 pop out of that. Some other tools that have proven to be pretty helpful are what are called 10-frame cards. And so here's one I did a search for just now. This one popped up on Pinterest. Some textbooks will actually have these sets of these come with them. Usually they'll be kind of like little plastic laminated cards, but you can just print your own. They'll last several weeks before the kids destroy them, even if they're on paper and cutouts. But I mentioned this the other day, that if you were to flash some dots in front of people, people can pretty easily see up to 5 dots and know it was 5. After that, it's like, oh, maybe it was 5, maybe it was 6. Maybe it was 7, I don't know. You get higher than that, then we just can't count that fast and recognize that fast. But if the things are put together so that there's always rows of 5, it's way easier to put them together and kind of figure out what's going on. So if we take, say, a block with 7 in it here, and a block with 8 in it, kids visualizing that in their head, that we're struggling to remember that, say, 7 plus 8 was 15, this pattern might help them see, all the 3 5s that make the 15, right? 5, 10, and then the other 2 and the 3 fit together really nice to get that 15 there. So anything we can help connect the words that we say, pictures in the mind, counting, making those connections in the brain, just will help people be that much better when it comes to doing other kind of math later on. Okay, so 10-frame cards are really cool. I've got a great workshop I do with like 1st and 2nd grade parents with 10-frame cards for games they can play at home with the kids to kind of make it a little bit more fun. Like 10-frame cards are great for playing like addition war, where you each throw it on the card, and the first one can say what it adds up to, is the winner, and they take the card. Right? But aren't regular playing cards pretty good for that too? Why are regular cards good for doing that too? Right? Because they have those little symbols on them, right? A 6 has 6 hearts or 6 diamonds. A 5 has 5 diamonds, so they can kind of look and recognize those patterns too. Benefit of 10-frame cards is it's always grouped by 5. Playing cards have some patterns that are nice and symmetric, but they're just putting them together is a little bit trickier. But it's still a cool thing to do. Okay, so we're going to play with our base 10 blocks. So what we want to do is, they give an example here on our first activity where we're going to show what 28 plus 34 looks like to come up with an answer. So at this point, kids have done a whole bunch of single-digit addition, so they can figure out through some model that 8 plus 4 is 12. How do we get them to then take the 20 and 30 and come up with a whole new number based on that? And so the trick is, what do we group by in our number system? We group by 10s in our number system. So anytime we can find a group of 10, we want to put them together. Now mine are arranged in a way that's hard to see, so I'm going to think about them like 10-frame cards so I can more easily tell how many's there. So would you agree with me this is more recognizable as 8 than the whole string of 8 things was? Because I had to count those. But here I can pretty much look and see, oh, 5 and 3 is 8. So again, it helps with pattern recognition. What do I need to make a 10 here? Yeah, so we had two more. So we know addition is combine and count, and so then we take 2 ones and group them with the 8 ones, and then we go to our bank of toys and we actually make that happen. So here I have my digital one where I can just highlight those guys, and now I have an extra 10. Okay. So instead of carrying, we're regrouping. So we just play that with the toys. So now what could I call 28 and 34? Yeah, I can see there's 6 10s and 2 left over, so it's got to be 62. Okay? No carrying went on there. All I did was regroup, put them together, and count them up. Okay. So drawing that on a piece of paper, you're going to have to do that for me someday soon. Let's see, where's my magic pen? I hang it up. Oh, it's hanging up there. Okay. Tools are gone. They are. So what I want to do again is I want to demonstrate 34 and 28. Drawing it on a piece of paper is way harder than showing it holding the toys, right? When you got the toys in your hands, it's super easy to demo. And then what you do is you get the kids to make up new numbers and have them show it on the desk and show their partner how to regroup them, okay? So, but we build up a little bit from there. So ultimately we want to work up to stacking them 34 and 28 to come up with an answer, right? So I demonstrate my 34. So 10, 20, 30, 1, 2, 3, 4, and then my 28. 10 is probably a little too long. 20, 1, 2, 3, 4, 5, 6, 7, 8. And again, when I have more than 5 ones, I like to put them in groups of 5 just to make them easier to see. And we know addition means combine. But we have a base 10 number system. So what we're going to do is we're going to take, again, those 8 right there and the 2 of these, and we're going to trade. So on paper, we have to make a note. Trade 10 ones for 1 10. So these guys are no longer part of my set anymore because I now have that new trade in here. And so combine and count. So I see 6 10s left and 2 1s. So there's my 62. Now, before I lead that into our regular carrying, actually, no, I think I'll just go straight to that. So what is 4 plus 8? It's 12, right? And so here, this trade in right here, right, that represents our regrouping. And so why do we put the 1 up here? Because that's our trade in up there. So what we do is we play the game with the kids first with the toys, and then we say, hey, that's our trade in. You just write it up there instead. And there were 2 1s. So we traded in 12 to be 1 10 and 2 1s. And again, how does the word 12 imply its meaning, that it's 1 10 and 2 1s? Isn't 12 a weird word? 16, that's 6 and teen is 10. Okay, but 12 is just weird. What's another weird word? 11 is weird, yeah, but 13, 14, 15, 16, those all make sense because really it's 6 and 10, 7 and 10, 3 and 10, so on. But 11 and 12 are bizarre, so we can reinforce that. Yeah, 12, remember, is a 10 and 2 1s. And then I have a whole bunch of 10s. How many 10s do I have in this column right here? I have 6 of them now, and so the answer's got to be 62. So this is now the regrouping algorithm, but we can still call it the carrying algorithm. And how many people grew up learning the carrying algorithm? Most people? Okay. So I'm going to show you a couple of other algorithms. So in this activity, what you're going to do is, I've got some dice up here. I hope anybody grabs some dice. You're going to make up a few more numbers, and based on those numbers, you're going to draw out a similar frame like this, showing your original numbers and how you're going to regroup them. Here they do it in 3 pictures. In my previous example, I did it in 2 pictures. It takes more than 1 picture to demonstrate this, because sometimes you have to regroup, and then you have to shuffle things around. So let me grab 2 and pass them around. So we're going to play with some dice. We'll do another one in just a minute. Before we do more of those, because that's kind of boring on video, I'm going to just demonstrate some other algorithms. So other addition algorithms. So you guys are all thoroughly familiar with the carrying or regrouping algorithm. And it scales up from the 10s to the 100s and so on. I think there's got a couple there, all right. So another addition algorithm is called the expanded algorithm. Expanded addition. So it looks like this. Let's use the 34 and 28 example. And it starts off the same way. What is 4 plus 8? We would say it's 12, but you write the whole 12 underneath. No carrying. And then expanded. Think about when we've used the word expanded in the last chapter. How does the word expanded relate to 34?
It's 3 10s and 4 1s.
Yeah, it's 3 10s and 4 1s. It just means expanded out. So with the expanded addition to work, you have to recognize that that's 3 10s and that's 2 10s. And so altogether, I must have 5 10s or 50. Okay? So we have to recognize place value for this algorithm to work. Then we have to reconcile our balance here. So basically, we end up with subtotals, and now we come up with the final total. 2 1s and no 1s, that's pretty straightforward. There's 2 1s there. And then a 10 and 5 10s is 6 10s, and so there's your 62. So there's no separating the 12 as a 1 and a 2, but you do have to recognize place value. So whether you're carrying or regrouping or expanding, you have to know place value if you really want to get it. And I could do that for any number of place values. So suppose I had 367, and I wanted to add 254. 7 and 4, well, that's 11. And so I just write it like that. And then that's really 60 and 50. 6 and 5 is 11, so that'd be 110, or 11 10s, right? And that's really 300 and 200, which altogether is 5 hundredths. And then since we're only doing 2 numbers at a time, we're not going to have to end up doing any kind of carrying. It's just going to work out nice. There's a 1, there's 2 10s, and there's 6 hundredths, so 621. Okay? So all I have to do is know place value. It is a great idea to put those zeros in as placeholders because we're emphasizing place value. I'll talk more about that when we do multiplication later. So that's expanded addition. All right. So next, let's do, oh, this is a cute one, lattice addition. So this is another algorithm. We'll pick on that same example, 34 and 28. So the way the lattice works is underneath these numbers, you draw a rectangle and turn that rectangle into 2 columns, so your 1s and your 10s. Then what you do is from the upper right to lower left, you cut diagonals through each of those squares. And So that's my lattice. And the way it works is, what's 4 and 8?
Or
12, yeah, sorry, the other one was 11, yeah. So this one's a 12. And the 12 just kind of fits nicely. It still looks like 12, the diagonal just separates them. 3 and 2, 5, and that's going to go in the lower part because it's not a 2-digit addition. Okay? And then you just follow the diagonals to get your answer. Right? So there's 1, 2, 3 diagonals here. So as I follow those diagonals, I get there are 2 in the ones position. The next diagonal are my 10s, and there are 6 10s, and there are no hundreds, so there's my 62. So it eliminates the need to carry. I still get to keep the 12 as a whole 12. I don't have to break it up into 2 parts in terms of regrouping. All right, let's try that one more time. What was that other example I had? 3, 6, 7, 2, 5, 4. All right, so give the lattice a shot, and then I'll write mine down, and we'll see if we agree on what the answer should be based on the lattice. So hopefully following those diagonals, you get the same 621 that we got before with the expanded method. All right, so note when we read a book, we read left to right. Other cultures that don't read that way? The answer is yes. There are some cultures that read the other way. So instead of left to right, they read right to left. Well, those same cultures also, but we do arithmetic, because the way we write our numbers, that we usually do right to left. Backwards is the way we read. So math is hard for some kids because with reading is hard for some people. That's one directional. But math, you have to move in all kinds of directions at the same time to make things happen. So there's a Hindu way of addition. Missing a letter. There we go. Hindu addition. Sometimes it's just called left to right addition. So let's take again our 34 plus 28. And again, most algorithms, you got to know place value, because place value is what makes our number system powerful and complicated. So instead of starting with the ones, I have to start over here with the tens. And so a 3 and a 2 is a 5, but I need to note that's 3 10s and 2 10s, which is 5 10s, so the 5 has to go right there. Then they move over to the ones place, and 4 and 8 gives me 12 ones. And what they do is on the fly, they cross out the 5, they bump it up to the 6 because of the 10 of 12, and then they write their 2 down. Okay, should you have done that in a different color? So the 12 comes down like that to get the answer of 62. Okay. Kristen's looking at me like that is so weird. It is.
It's not effective. It's harder to teach than it would be to just go.
I don't know. Carrying is pretty darn weird. All of a sudden you're telling me to put this other digit up on top. It's like, what? So I think people who grew up doing the Hindu would look at you carrying that 1 up there and say, why the hell would you do that? Just keep everything down there, right? And then other people grew up learning how to do the lattice, okay, or expanded. Okay, there's a lot of books you will see the expanded in there before they move on to the carrying. Okay, they kind of develop it in stages in some textbooks. Let's take that other example. What was it? 3 6 7 2 5 4. 3 6 7 2 5 4, and let's see if we can add these from left to right. And again, place value is the key. That's really 300s and 200s, so the 6 has to go in that same column there. 6 and 5 is 11, but I got to keep in mind that's 11 tens, or 110, and so the 100 part has to jump over here to make that 6 a 7, and then the other 110 goes there. Question?
Shouldn't it be 6? It should be
Oh God, it should have been 5. Thank you. Having one of those days where times and addition are interchangeable. All right, 3 and 2 is 5, not 6. Thank you. And then here, that's going to become a 6 and a 1 in that next stage. Thanks, Tiffany. And then we move over to our 1s, and 7 and 4 is 11 1s, and so the 10 from the 11 has to jump over there, and the 1 stays behind. And so that's how they would illustrate to get the sum of 621. They just move from left to right. Turns out we can do subtraction that way too. We'll try that later, maybe tomorrow or Wednesday. So all over the world, there are different ways cultures do this. The way we do it isn't the only way. It's not even necessarily the best way. We're just used to it, okay? And that's the biggest thing. Are there people who struggle with that carrying when they're young? Yes, I remember struggling with it. Maybe playing with the toys would have helped me. I didn't have toys when I was in school. Maybe that expanded method would have helped me figure it out better. But we do have a lot of people that struggle because this is complicated, simple manipulation here. Okay. All right, let's see. Those are the main algorithms for addition. Let's take a quick look at subtraction for a few minutes, and then I'll leave some time for you guys to work on activities together. So let's take a look at activity 2. So note here, the purpose of this one is to do takeaway and comparison. And the pictures look different. With takeaway, it's a single set that stuff gets chopped out of, right? So here we're Xing things out. With comparison, which is on the next page, I have 2 different pictures of the set. So instead of crossing them out, I have to show the first set and I have to show the second set. Now, in order for these to be comparable, I have to do some trading in, okay, because there's not enough 1s to compare these to each other. So that's borrowing. And then we see how they line up. And so it's kind of hard to see on this sheet, even if I zoom in. Hopefully yours is more readable. But they've darkened some of the squares in that last picture. So they picked up these guys down here and they stuck them on top. So the dark ones are where they match, the light ones are where they don't match. That would be the difference. Okay. On a piece of paper, I usually draw lines connecting them, and whatever's not connected has got to be the answer. So I'll draw a picture of that in just a minute. All right, so let's make up a number to play with. So let's see, can everyone roll their dice right now? Hopefully we'll get some numbers that'll be fun to play with. All right, we have a 66, is that right?
Yes.
Not 89. I guess the kids will call it 66. And a 51, 52,
61.
61, 33. 33, oh boy. I guess we can do 51 minus 33. Okay. So we'll draw this in 2 different ways. So we're going to look at 51 minus 33. And ultimately, what we want to work up to is our borrowing algorithm, which is also a regrouping. So we're going to write it out that way in a moment. So first, we have to get out our toys. So get 51 with your toys, and then get 33 with your toys. I'm going to use my virtual ones because they draw better. So 50. 1, 30, oops. Here. Click. Got it. Okay, so 1, 2, 3, 51, and there's my 33. So at the moment, if I wanted to do, I guess I set myself up to do the comparison. So we'll do that first, even though the activity is takeaway first. So showing both sets means I set myself up for the comparison model because I want to see how they line up. And the problem I have at the moment for this is that they don't line up because one group does not have enough ones to compare to the other group. Right? So that's a problem. So we're going to do some regrouping. So how are we going to do that? Yeah, we take one of the 10s up here and we break it into 10 pieces. So trade in one of your 10s for 10 pieces. So let's see, that is this tool, I think. Smash. There it goes. Let's see, can I then select some of these? Oh, that's nice. Do that. So this is still 10, 20, 30, 40, 51, but now I've set myself up so I can compare them. So stealing a snapshot of that. Throw that right there. Okay, so I'm just going to make a little note on my paper. Trade 110 for 10 ones. And so then I do my comparison. So these guys line up, and those guys line up, and those guys line up, but then I run out of 10s to compare, and then I start comparing the ones. So again, we're doing comparison here. What does that leave? Well, it looks like we have a 10 and 1, 2, 3, 4, 5, 6, 7, 8 ones. Is that right? So that leaves 1, 10, and 8 ones, or 18. So then with the kids, we do multiple versions of this so they get used to that. And then we come over here and say, okay, can we compare 3 and 1 directly? Answer, not enough ones, okay? So what did we do with our toys? We traded a 10 for 10 ones. So we say, okay, well, that means this is now going to become 4 10s, and we move 10 ones over there, so now we have 11 ones. And they have those toys that show, here's my 4 10s, here's my 11 ones. Right, so we're illustrating that. Then it becomes pretty straightforward. 11 take away 3 is going to leave us 8. 4 take away 3, 5, yeah, 4 10s take away 3 10s, leaves us 1 10. And so we're kind of motivating why we do all this crazy crossing and moving stuff over, because we have to compare them. Okay, so here's your goal next. Draw what you think a takeaway model for 51 minus 33 would look like. And you can use as an example that first page of activity 2 where they show what it looks like for 43 minus 28. Actually they show 2. They show 34 minus 10, which is pretty straightforward, and then they show 43 minus 28. So you want to draw a similar picture and use the toys to demonstrate 51 minus 33. So first do it with the toys, and then draw a picture of it. So there's my version of the drawing. You can take a look at it after you do yours. Just so finish up yours, and we'll talk a little more about how they're alike and different. So with the takeaway model, I only draw the top number, the first number. I don't draw the second one. And I just look at it and observe, can I just take away here? Now at this point, I can't cross out 3 ones because there aren't 3 ones to take away. So that's where we have to trade in, or what we call borrowing. It's really trading in. So I trade 1 10 for 10 ones, and now I'm in a place where I can get rid of the 3 10s and 3 ones. So I just do it, cross them out. And then I just look and observe what's left behind. Well, I see 1 10 and I see 8 ones. Same result in the end, it's just a different means to get there. So takeaway model, I only had to draw the original number and then cross out what I'm trying to subtract. With the other method, I had to draw both numbers so I can line them up and compare them. Okay. Some people like the takeaway better than the comparison. Some people like the comparison. Okay. Kind of depends on the person. All right, so I'm going to show one more example, and then I'm going to set you guys free right now to work together and get some of these 2 activities done. We do borrowing, which is also called regrouping or trading in, depending on what book you see it in. But that's not the way everybody does it in the world. There's a lot of other ways to do subtraction. And so I'm going to demonstrate my favorite way for 51 minus 33. So here's the story I tell myself when I do it. I'd like to take 3 from 1, but I can't. And I say, wouldn't it be nice if that was an 11? Now, to do that, that means I have to add 10 to the top number there, right? Because that was 51, now it's 5 and 11. So what I do is I add 10 to the bottom number, but I put it in the tens place instead. Okay, so what does 11 take away 3? On a good day, that's 8. And what does 50 take away 40? 10, and so there's the answer, 18. This is called the equal addition algorithm. So I'll demonstrate it one more time, and then next class I'll explain it. There are variations on this like there are on most algorithms. And subtraction's pretty rich. There are a ton of different subtraction algorithms. We'll go over a few of them together. So maybe the numbers were 34 take away, I don't know, we'll go 17. And so this is just an alternative to borrowing. And again, I can't take 7 from 4, so I just add 10 to the top number by making the 4 a 14. I add 10 to the bottom number by changing the 10 in the bottom to a 20. So my equal additions are, I added 10 to the top number and I added 10 to the bottom number. I just did it in a slightly different way. 14 minus 7 is 7 on a good day. 30 minus 20 is 10. So the difference ought to be 17. Double check. 17 plus 17 is 34, so it works. So you might look at this and say, that's nuts. I already know how to do it. I love borrowing. Leave me alone. This has benefits that I'll explore in the next class. I'll also explain why it works if you haven't figured that part out yet. With the models, that's where we really, you guys need to have a very clear vision as to why those models are useful. For the algorithms, I don't necessarily need you to explain why the algorithms work. I just need you to try them. And so like what a test would look like in the future is I would say, okay, demonstrate a couple of different ways to explain why 7 plus 8 is 15. So then you would say, oh yeah, I can show you with sets, or I can show you with the number line. And then I would also say, take 34 or take away 17, show me a couple of ways to make that happen with algorithms. And we'll look at some more algorithms next class. But I just wanted to leave with that because I think this is a fun one. And again, it does have some benefits that in certain problems make it way easier to use than our borrowing algorithm. So we'll take a look at that next time. All right, let's back up, take a look at some of the requirements for these activities, and then we're just going to get some stuff done right now in the last 10, 15 minutes of class. So in activity 2, and I guess, yeah, I'm going to go from activity 2 and then back up to activity 1. You're going to roll some dice and make up some different numbers to play with, and then draw out your pictures. So you'll have a couple of pictures for, there we go, zoom out a touch. You'll have a couple of pictures for subtraction using takeaway. On the next page, you'll have a couple of pictures for subtraction with comparison. And you're also going to write a couple of word problems. So like you already wrote a word problem for takeaway, right? I think everybody in here wrote takeaway. I wrote a comparison one. And the problem with Ruby in the car, that's pretty much a comparison one too, although it can be written a little bit different. So you'll have some pictures, and then you'll have the story problems. The story problems, you're just writing me a story. You don't have to draw me a picture. Okay, so it's just coming up with a story there. And then here they demonstrate some other algorithms, and so you're going to play with those a little bit. Backing up to activity 1, and I heard some rolling of the dice earlier, so I think people are probably getting a head start. Pretty similar, you're going to roll the dice to come up with some other problems. We already did one together, or we did the 28-34. Okay, so you got to do 5 new ones. And then here they call it carrying, right? That's what I grew up calling it, didn't you? The more politically correct way to call it is either regrouping or renaming or trading in, you even see sometimes, because that demonstrates the physical aspect of what's really going on in the background, why it works. And so here they just want a little explanation, kind of like I gave, about why would we call it regrouping instead of carrying. And then otherwise over here, they show some different ways we might add numbers other than the standard one. Right? And then with the last part here, based on these different strategies, left to right, decomposition, nice numbers, compensation, demonstrate some of those using these problems below. Okay. And so you'll have to look at, say, 413 plus 289. Would that be a good decomposition, or left to right? Just give it a try and see what happens, just to get used to putting numbers together in a slightly different way. Okay, so I'm going to shut up. I'm just going to walk around and help people that have any questions.